Good evening, everyone. Welcome to the second session of Mathematics Week. And today we will have two sessions. In the first session, Professor Emre Alkan from Koç University will be with us. Also, I would like to thank Emre Alkan on behalf of both universities. And now we leave you with prime counting functions and combinatorics.
Thank you very much for this opportunity to speak. So today I will talk about prime counting functions and, more important than that, some natural connections to combinatorics. So let me start with some definitions. So I said prime counting functions, but mainly I will deal with only this function, the usual prime counting function, which is counting all the primes. So pi x is the number of primes not exceeding x. So x is a given quantity. I mean, of course, to make sense, you take x to be greater than or equal to 2. And then whenever you see a prime, you count it. Okay, so you get this function pi of x. And well, it's natural to also look at this function sometimes. If you are thinking a little bit probabilistically, then, well, what is the probability of finding a prime number if you make a choice among the numbers, positive integers up to x, then that's the probability approximately, of course, of choosing a prime. So that's a significant function. So if you normalize and divide by x, you call that the density function. Okay, so and you can call this the px. So if you want to think of in terms of probability, then this is a function that you consider. Okay. Now, first of all, a milestone in the study of pi x and the set of prime numbers is this result, which is called the prime number theorem. So, and it's as follows. So it says that pi x is asymptotic to x over log x. So with the meaning that the ratio, if you divide pi x with x over log x and let x go to infinity, then the limit is 1. So that's the meaning of this. So we just simply show it with this notation. So pi of x is asymptotic to x over log x. Generally, that's how the prime number theorem is stated. But of course, there are alternatives. So I will first show you just as a little warm-up. Equivalently, we can state this in the following way. So we can look at the limit of x to the power px. So let's bring in the density function into the game. Now it's easy to see. I mean, it's really trivial what we are doing here. So just put what px is. So this is limit of x to the pi x over x. And if you write x as e to the log x and just write the log below, you get this limit. So it's limit of e to the this. But of course, this limit will be e. And because by the prime number theorem, this tends to 1 as x tends to infinity. So this limit will be e. And conversely, I mean, if this is e, then you get the prime number theorem. Okay, so this has to tend to 1. So equivalently, you can state the prime number theorem in this form. So limit of this quantity is e. Now, that's a little bit nice because you see e is a very important number. It's related to, I mean, one can say everything in math. And it's pleasant to see that e is related to somehow the distribution of prime numbers. Okay, so it's related to this limit, and this limit depends on, of course, pi x, so the counting function of primes. So that's why it's pleasant to see e there as coding some information, I mean, about primes. So in fact, you can get excited about this a little bit, and you can say maybe we can approximate e, the decimals, by information on the primes. So using tables of pi x. of course, there are tables of prime counts up to very large numbers now, nowadays, of course. We can get them by computers. And in fact, I tried a little bit here. So I took some values from the prime counting, for the prime counting function from the tables. So in fact, it's a quite huge number. So the number of primes up to 10 to the 10 is this number. Okay, so that's the count. So you can try to form this quantity. So I divide it by 10 to the 10. So one gets this number. Okay, and then I take 10 to the 10 and then exponentiate that like this. And one can calculate this number. So you get this 2.85136. So something like this. Okay, let me recall that the value of E, I recorded some decimals here, known decimals. So 2.7182. So it's quite far off, as you can see. I mean, we can match only the integer part here, but the others don't match. I mean, it's quite a huge number. Okay, and in fact, I took one more step. So I looked at the table at 10 to the 11. So that's the count of primes up to 10 to the 11. And if you carry out a similar calculation, you get this number, 2.837. So there is a decrease, as you can see, a gradual decrease. Hopefully you will get to this. I mean, it's guaranteed, but I mean, one shouldn't get too excited about this, maybe. It's theoretically interesting, but it's not very promising numerically. And that's due to the fact that limit is taken very slowly here. I mean, quite slowly. I mean, the prime number theorem, the limit of this ratio is tending to 1 very slowly. So that's why even with such large numbers, we still are far from the actual value of E. I mean, we can't still match the first digit, as you can see here. So obviously, this is not a practical way of approximating E, but it's nice because one would like to see that E is related to the distribution of primes. So one can do it trivially like this out of the prime number theorem. So as an equivalent way of writing it down. Okay, now I would like to continue with the following. Now, of course, prime number theorem tells us that, well, the limit of the ratio is 1. So in some sense, well, how good is x over log x as an approximation to pi x? Well, it's only in a multiplicative way here, okay? So, and now this is, if you want to have a better form, of course, there is strong form of the prime number theorem. So, and I should definitely go into this now. So one can prove that, so indeed, pi of x is equal to, well, now the shape of the formula is a lot different. So there's a main term. So this is Lix plus some error term. And the order of the error term is this function, x divided by some exponential e to the minus c square root of log x. So this formula is true. So for large values of x, indeed as x goes to infinity, and c is a constant that you get here, okay, through the proof. So we don't specify what c is in our arguments, although one could give values, but we will not do that. So c is positive, okay. Of course, you should ask what this is. And the O notation is a familiar notation in number theory. It says that the function that's hidden here is the absolute value of that function is always less than or equal to a constant times this function. Okay, so the constant is unspecified. So we just write it with the O notation. So you can see that there's a function whose order is really about this function. Now, how about this function, Lix? So it's defined like this. Lix is this integral from 2 to x of 1 over logarithm of t dt. So we are simply integrating 1 over logarithm of t from 2 to x. And that's called the logarithmic integral for obvious reasons, because it involves the logarithm. And one can see somehow that, well, if you look at the function pi x over x from this, if you divide by x, well, the density of primes is like 1 over log x. So it's asymptotic to 1 over log x. Well, it makes an appearance here. I mean, that's the density indeed, and I'm integrating the density. So that's like, in some sense, an average value, so that the formula improves. So that's why it's a strong form of the prime number theorem. So that seems to be a better approximation to pi x. Now, this time it's additively a better approximation, not multiplicatively, because I'm adding here, and it's now an additive approximation, as you can see. So this is called the logarithmic integral. Now, one little remark about this. This looks like a calculus type integral, of course, but you cannot integrate this. Okay, so like you do in calculus, you cannot write down an antiderivative, useful antiderivative for this, plug in x and 2 and get a formula. So it's impossible. So that's a theorem, which I will not, of course, get into here, but you have to leave it like this. Okay, so that's called the logarithmic integral. But you see, really this shape of the integral is very useful. Now, it's very nice that we cannot get it as an exact formula, but we can do other things. And by the way, there is also some freedom in the lower limit of this Li. I mean, some people define the Li with different lower limits. It depends on, on the context. I mean, you could start at 0, but then you could worry about improperness at 1. Okay. I mean, I think this is a natural choice because some sense primes start at 2. I mean, you don't see any prime before 2. So that's the natural lower limit, it seems. So that's why I stick to this here. Although one could change that a little bit. That depends on your purpose, but that should be fine for us. Okay, so of course, if you change the lower limit a little bit, that will bring in some constants here, which you can always bury into the O term. So that wouldn't make a big difference for us here. Now, although you cannot evaluate this like a calculus integral, you can integrate by parts here. Okay, so you can integrate by parts. So, and then you easily get this. So Lix is x over log x minus 2 over log 2. So the evaluations at 2 and x. And then if you look at the integral after integration by parts, you get plus from 2 to x 1 over log t squared dt. So instead of 1 over log t, you have 1 over log t squared. So you see, then you have an improvement here. Now, of course, you can put this formula into the strong form. You can replace Li with this. And no surprise, of course, as your first term, you see x over log x, making an approximation. But now this says the following. If you look at the difference between pi x and x over log x, now you can kind of see it if you just take the difference. So between pi x and x over log x, well, on the right-hand side, you have this constant, you have this integral, and you have the O term, okay? Now, but if you look at it, I mean, if you look at the size of this integral, it's not hard to get the size of this integral. Log t, I mean, changes very slowly. If you truncate very near to x, one can see easily that this thing is approximately x over log x squared. So that's the contribution really of this. So then this means that x over log x, this term is not a very good approximation to pi x, okay? So in an additive way, because if you look at the difference, pi x over minus x over log x, this can be as large as the order of x over log x squared, namely this integral, because this constant is insignificant there, and the O term is insignificant when you compare it with this integral. Why? Because of the exponential term. I mean, one can easily check that this exponential term, e to the minus c square root of log x, dies very fast with respect to any negative power of logarithm. So that's the little o notation. So this means that this is a lot faster tending to zero than any negative power of the logarithm. Hence, of course, this function is a lot smaller than x over log x squared. So this means that pi x minus x over log x can be as large as this, x over log x squared, but that's still large. Okay, so this means that that's not a very good approximation to pi x. Although in the ratio sense, it's okay, I mean, but additively, it's not that good, okay? And this simple reasoning just justifies that and warns us in that way. But now, although that's what we get out of this, now we have a very nice formula to work on. Now we can repeat integrating by parts here, and indeed we can improve on this formula, the strong form of the prime number theorem. So in this way, we can get an asymptotic expansion by repeating this. Indeed, we can say that pi x is given like this. So it has this asymptotic expansion. K goes from 0 to infinity, and the terms look like this: k factorial x over log x to the power k plus 1. Now, the meaning of this is that if you truncate this, let's say at n minus 1, and look at the difference. So pi x minus just this sum from 0 to n minus 1, and these terms k factorial x over log x to the k minus 1. Now, this difference is asymptotic to the next term in the expansion. So really, the next term in the expansion is, well, you take n here, n factorial x over log x to the n plus 1. So asymptotic, of course, I showed it like this. So the ratio tends to 1. So I called it 1 plus O1. So this tends to 1. So I showed it like that. You can call this either the error or tail of the expansion. So, and you can do this for any positive integer n, okay? And so you get really a family of asymptotic formulas here. You can do it for any positive integer. So they become meaningful as x tends to infinity, okay? So we have to take the limit. But now I should tell you that asymptotic expansions, of course, are very different from power series expansions, for example, that you see in calculus. So I should say that asymptotic expansions like this one, they are not useful for fixed x, okay? So, and you can really see it here. I mean, if you fix a value of x, like say that x is 1,000 or 1,000,000, whatever you fix it, okay? Now you can look at seemingly the tail or the error. If you look at this term, and if you let n go to infinity, like you want to do in power series, I mean, this thing tends to infinity, right? Because x is fixed now. So the factorial always, when you divide it by a fixed number to the power, you can see that this limit is infinite. So when x is fixed. So, well, you see that unlike in the case of power series, I mean, the tails don't tend to 0. I mean, they can tend to infinity for a fixed x. So it's no good for fixed x, okay? So that's why it's called an asymptotic expansion. So things become meaningful only x goes to infinity, okay, in the limit. So that's what I want to say here, just to distinguish an asymptotic expansion from the ordinary power series expansions, okay? Now I come to my main point. So I will start to now use this expansion and show you some interesting combinatorial connections, okay? At the outset, of course, I mean, what could be a connection here? So that's that's in fact my main point, my main goal in this talk, just to show you some combinatorial connections. So I would like to start with an appetizer from Ramanujan, okay, to make this clear. So Ramanujan really takes n is equal to 5 in this formula. So just take n to be 5 here. I mean, you can take n to be any positive integer, but specifically you take n to be 5. You will see a little bit the reason why we want to take 5. So when you take n to be 5, you can write pi x like this. So k goes from 0 to 4, k factorial x divided by log x to the k plus 1. So there are some, there are just, as you can see, 5 terms here. And then you have the tail. But you can always write the tail as an odd term. I mean, I will not write it as an asymptotic, but I will write an odd term. Definitely the tail, now I can bury the factorial inside the O now, because I'm fixing the n now. Okay, so I can write an O for that. And I can write, of course, when I take n to be 5, I have to write x over log x to the 6. So that's the order of the error, okay? So, and I can take, I can say that this is true for all large enough x. Okay, so I can use that for all large enough x. Now, Ramanujan takes n to be 5, but that's not the whole point. He wants to consider pi at x over e. I mean, so you see Euler's number now makes an appearance. He wants to find this. Now, what do? You simply take x over e instead of x, just put it here. So, of course, there is a nice thing about logarithm. Log x over e becomes log x minus 1. So you have this. But when you put x over e here, I mean, you don't need to change anything because the differences you can bury into the odd term. So there is not much of a difference here when you replace x by x over e. I mean, you can change the constant. You can shift the constant a little bit and you can bury that. So this term is not affected by this change of variable there. But now one thing stands. How do I do that? Now, log x minus 1. Of course, one can easily write it in the following way. Okay, so you can factor the log x. So you can write k factorial x e times, you can factor log x to the k plus 1 and get this 1 minus 1 over log x to the power k plus 1. So that's easy. And I just repeated the error term here. Well, what can I do about this part? Now, that's something familiar. So that looks like a geometric series, but it's a power, but we can easily handle it, right? So we know that by differentiation, by repeated differentiation of geometric series, you can easily get this thing. 1 over 1 minus 1 over log x to the power k plus 1. You can get, in fact, this time, the power series expansion of this. So when x is large, this is small. 1 over log x is small, so this becomes meaningful. So you get this. I mean, this is well known. So you get this power series. Okay, so m goes from 0 to infinity. You get the binomials, so which is a natural object now in combinatorics, of course, and 1 over log x to the m. Okay, so that's easy by differentiation of geometric series. But once you have that, you can insert it here, and you can do things. So pi of x over e, you can insert the formula, and you can insert this formula and just multiply with the other terms. This is what you get essentially. So k goes from 0 to 4, then m goes from 0 to infinity, and you see the terms. The binomial, k plus m choose m, k factorial x, e, and then what is the net log x power? Log x to the m, but there's a k plus 1. So that's what I should write, log x to the m plus k plus 1. And I repeat the error term next to that. Now, one thing stands here. Now, as soon as m plus k is greater than or equal to 5, all the terms, I mean, you can make a truncation indeed in the power series. You can make a truncation, and as soon as m plus k is greater than or equal to 5, this is greater than or equal to 6. So you can bury that into the odd term. So all terms here really with m plus k greater than or equal to 5 can be absorbed into the odd term. So that's clear. But then you have finitely many terms left. So this means that we may definitely assume that m plus k is less than or equal to 4. So in this way, of course, you can write all the terms very clearly. Okay, you can calculate the binomials. I mean, there are finitely many choices of m and k here. Okay, with m plus k less than or equal to 4. It's a little bit painful, but you can write all the terms, okay, with explicit constants. And in this way, we can write pi x over e explicitly. Okay, I will not bore you with that calculation. I mean, it's trivial. Once you get to this point, you just calculate and write all the terms, okay? And the rest is just error term. So you get x over log x to the 6. That's the order of the error term. But now what Ramanujan did is make another observation. So this was a suggestive calculation, but what is the point after all? I mean, what do we do with this? Now he observed that now if I square pi x, so you can do a similar calculation going back to this. I mean, you can square it. So you can take this. So how many terms are there? There are 5 terms here and 1 error term. So you can square this. So of course, when you square, you can square 1 by 1 and find mixed terms and of course collect terms together and collect them under the old term. So you can square this. It's not very difficult to do, which I will not do. Okay, it's boring calculation, but nevertheless, there is a point in that. Once you do that, you can get a similar expansion like in this one, okay? Now you can sense what will happen. At least you can sense the following here. So when you square things, so you can see what's going on somehow. So you can square it. And then with this formula, you can multiply it with ex log x, okay? So you take this and multiply everything with ex log x, and then you subtract. Now, I will not go through that calculation, of course, but if you do that, I mean, lots of things cancel out miraculously, I should say. And that's the whole point of Ramanujan. So up to the power 5 of the logarithm, everything cancels out, okay? And then you get this interesting outcome here. Of course, you can sense that when you multiply this by x over log x, you multiply here with x over log x. So you would sense that the error would be of this order, x squared over log x to the 7, because I'm multiplying with x over log x here is not that important because I can bury it into the old term. So that would dictate the error term. I mean, of course, from pi x squared, it's not that significant. I mean, it would be buried into this, the error term coming from this. In any case, things cancel out, but only at the 6th power, they don't cancel, but you get this. So when you calculate this combination, by the way, it's now a nonlinear combination because I'm squaring pi, the function. It's really a nonlinear combination. So Ramanujan really breaks the linearity as well here and looks at this interesting function. Somehow he was able to see that. I mean, everyone can check, of course, after this point that you get this. Now, what is the point, of course? This is a lot smaller than that because this is log x to the 7. So when x is large, of course, watch the minus sign, this will become negative, okay? Whatever constant you have here, once it's, so it's fixed, okay? So when x is large, this term is a lot smaller than that term, but this is a negative. So this means that this will be negative. So he proved that really then this term exceeds pi x squared. So he got an inequality here, which interestingly takes this structure into account, okay, this asymptotic formula, and makes this possible. In fact, what is so specific about Ramanujan's choice of dividing by E? Now, I think a result of Hassani from recent literature makes this very clear for us. Now, Hassani showed that if alpha is a number greater than or equal to E, then look at what he proved. Pi x squared is always less than alpha x over log x times pi x over alpha. This holds for all large x, okay? And I think the case when alpha is equal to E is Ramanujan's inequality. okay? So it's just an extension of Ramanujan's inequality, but he also can explain why he chooses the E, okay? Because he also proves that if alpha is less than E, if it's a parameter that's positive and less than E, then this inequality reverses, okay? So it's no longer true, so this becomes bigger than this. So then this means that indeed Ramanujan's choice of alpha is equal to E was optimal. I mean, he found the optimal number here, the smallest indeed, such that this thing is less than that. Okay, so I mean, this is really a great insight here. Although it's a miraculous calculation, I mean, that's what the ingenuity is. I mean, finding it out. So really, it just depends on simply using the asymptotic expansion and working it out. I mean, but you should definitely beforehand have some feeling on what could happen out of this. I mean, you can say I can divide by maybe E square here and get similar things. It doesn't happen. I mean, doesn't happen. Really, there is some miraculous insight there, which makes this possible. And Hassani's result really explained this. But now one is really inspired by this evaluation of Ramanujan. So that's now what I would like to talk about next. So maybe, in fact, I already offered it. We can maybe do other things, okay? Instead of dividing by E, let's multiply by E. Anyways, maybe we can get a similar calculation. So that's what I tried. So in a similar fashion, you can look at pi of E times X, okay? So imitating Ramanujan. Now I worked it out. In fact, you get a nice thing. I mean, I will not show you the calculation. It's just algebra. So, but you can sense what will happen because you get log EX at this point. So this will become a +1. So instead of -1, I will have a +1. That would be the only difference. But then I can get similarly the geometric series trick. So this will be a plus. I can work it out. I mean, there will be a sign alternation in the power series, and you can work it out. I mean, it's not difficult once you have the inspiration. So I worked it out and I got this. So in fact, I got the asymptotic expression. Look how it is. So dn ex over divided by log x to the n+1. Okay, so of course the appearance of ex is natural because I have an ex here. But what is this dn? Okay, so where it turns out that dn is the number of derangements of this set of positive integers from 1 to n. So if you don't know this word, I can easily tell you derangements is exactly this is the number of permutations fixing none of these numbers. So none of the points is fixed by the permutation. So it doesn't send 1 to 1, for example, or 2 to 2. Okay, so any such permutation is called a derangement. So dn counts the number of such permutations. So it's nice to see it here. That's a combinatorial object, obviously, okay, because it's related to permutations, a specific type of permutation, and it makes an appearance. Now, it's always, of course, a problematic thing. What happens when n is 0? Because then you don't have really the permutation here. You don't have the set when n is equal to 0. Well, it's just you want to define it to be 1. I mean, to be consistent with the theory of count of primes. Of course, you want to take d0 to be 1. And that's what is done in, for example, in generating function theory. So d0 is taken to be 1. Okay, so that's a convention that we make. Other than that, we have the number of derangements. So number of permutations here fixing none of these points. Of course, it's easy to find dn also as a formula. You can easily do it by the inclusion-exclusion principle. I mean, so you can just, since it fixes none of the points, I mean, you can consider permutations fixing 1 point, 2 points, 3 points, and things like that. And you can use inclusion-exclusion principle. and it's easy to find the number of permutations fixing some of the points. Okay, I mean, you can easily find it. So dn turns out to be like this. It's n factorial times this sum. K goes from 0 to n minus 1 to the k divided by k factorial. So that's the exact formula for dn. So you can put it here, in fact, and you can see the factorial, in fact. I mean, of course, the factorial should make an appearance somehow. It was because it was appearing in the earlier formula. I mean, there were factorials here, as you can see. So, but nevertheless, it's tilted a little bit because I'm multiplying it with this now. So just for the fun of it, for the enjoyment, I have calculated some derangement values here. Okay, so D0 is 1, of course. D1 is 0. I mean, there is no derangement when n is 1. Okay, 1 is fixed anyways. So D2 is 1 and D3 is 2. You can calculate it from the formula, I mean, with some effort. D4 is 9. D5 is 44. D6 is 265. So as you can see, there is a rapid increase, and because of the factorial, of course, okay? And then you can continue like this. So I gave some values. Okay, so that's one thing one can do. Now, in fact, I have written here another sequence for you. So here is another sequence that I offer. A1 and A2 are 1. A3 is 3. A4 is 13. A5 is 71. A6 is 461. A7 is, well, it's huge, 3,447. Now you see, I mean, we can ask ourselves, can you tell what's the next term? I think that will be a tough question. I mean, what was the pattern here? Okay. Of course, for the derangements, we have a pattern, we have a formula, we can find the next one. So I just for the fun of it, so don't worry. I mean, if you cannot tell what it is, no one could tell maybe, but it's this. A sub 8 is this. It's even a lot bigger, as you can see. I think it's 29,093. I mean, who could have calculated the next one? Now you can ask, what is this sequence? So I can tell you that AN is the number of indecomposable permutations of 1 to n. Now, what is an indecomposable permutation? Now, it's simply like this. A permutation tau is indecomposable if tau sends when m is less than n. Tau does not send this set to this set. Okay, so it doesn't fix this as a set for no m less than n. Okay, so such permutations are called indecomposable. For example, let me just tell you an indecomposable permutation. If you just write these numbers from left to right, like n minus 1 dot dot 1, so 1 is sent to n and 2 is sent to n minus 1 and so on, that's definitely an example of an indecomposable permutation, because then this never holds. Because in this, you see tau sends this, definitely, and there will be the n here in the output. So you cannot have this for for any m less than n. So you can write examples of indecomposable permutations, definitely. So this means that tau never fixes this set when m is less than n. Of course, tau fixes the full set. I mean, that's obvious, right? Because of being a permutation. But it doesn't fix when m is less than n. So that's an interesting condition. And one could just ask, I mean, what the hell? I mean, what is interesting? What could be interesting about such a condition? I mean, it's very restrictive and strange condition, it seems. But I can tell you that there are lots of interesting things about this. A famous mathematician who has a book in combinatorics, Comtet. So here's a book, very useful book in advanced combinatorics. He was the first to show that indeed one can do a lot of arithmetic with these numbers. so the number of indecomposable permutations. So he proved this, for example, that when you take the ratio of an to n factorial, it's 1. So this means that that's the number of all permutations. So really, this means that there are lots of indecomposable permutations because the ratio tends to 1. So that's quite an interesting result on its own. So one can say that in some sense that almost all permutations are indecomposable. So this means there's a lot of them. I mean, the majority of permutations will be indecomposable. And it's not a priori clear why they should be because of this condition, but that's what it is. And he got a recursion formula for the ANs. So this sequence has some structure. So AN is n factorial minus I goes from 1 to n minus 1. Okay, n minus I factorial times AI. So it's a complicated recursion. So AN depends on all the previous terms of the sequence. So it's a complicated recursion, as you can see. But now, what is the connection? I mean, this is combinatorial significant object, definitely. Okay, but what is the connection to prime counting functions? Now, another miracle happens here. So I will now connect it. I mean, it may not occur to you, maybe why, but here is another miraculous connection. So I will look at pi x over x. So from my earlier asymptotic expansion, I will just divide things by x. So I will erase this x, okay, and write it as an asymptotic expansion. So you just write it like this. In fact, there is a 1 over log x common factor. I pulled it out. Remember, I was writing k plus 1 here. So I pulled the 1 over log x. So I'm allowed to write k. So, and I truncated that. I'm using a different letter now. I used m. So I truncated at m minus 2. So the error has order now 1 over log x to the m minus 1. So there is no x because I divided by that. So I can go with this formula. Okay, so it's the formula that I get easily from the earlier asymptotic formula. And m is any number. Let's just say when this is meaningful, you can take m to be any number greater than or equal to 3. Now, what I do is I formally will invert this. Okay, so when I invert it, so I will take capital X as 1 over log x. So this looks like a polynomial then. If I think of 1 over log x as capital X, so this is like a polynomial and there is an error term. Okay, there is an error term. So then this means that I can invert a polynomial. In fact, I can think of like inverting like a power series, and I can invert a polynomial. Not only formally, but theoretically, you can also justify this, which I will not do. But just imagine that formally you invert this and then try to find the coefficients. Of course, if you invert here, you get x over pi x. Now, when you invert here, you get a log x. Now, of course, when you invert here, so this O term will look like 1 plus the same type of O term. Remember, capital X is 1 over log x. But then you have the inversion of the polynomial part here. So, well, then it will look like this. It will look like a polynomial like this and goes from 0 to m minus 2, some coefficients and x to the n. Okay, so of course, when you multiply them, you have to get somehow 1, right? That's the inversion apart from the error term. So this means that B0 has to be 1, but the rest should be 0. So the rest should be 0. So when you multiply, you have the, of course, the convolution structure. When you multiply two polynomials, okay, so you have the convoluted structure here, but none of the terms will be non-zero because you want to get 1. That's the meaning of inversion. So now you have this condition on the coefficients of this inverted polynomial, okay? So they will look like this. I goes from 0 to n minus I factorial, because y factorials, because they are the coefficients here for this polynomial, and the bi's are here. So the convolution will give you 0, okay? And that's true for all n between 1 and n minus 2. But now one interesting thing happens. This looks a lot like this formula. Okay, so there is this convoluted structure also. Apart from this thing, which is easy to fix. In fact, you can do it in a moment. So in fact, if you calculate B1 and B2 easily from this, you get -1. So that tells you that it's good to define minus of the BNs here as AN star. So for n greater than or equal to 1, I define minus BN as AN star. Then what can I say about AN stars? First of all, A1 star and A2 star are 1. And then if you insert here as BN as minus AN star and work it out, you get this formula. I just separate the I is equal to, for example, 0 term and I is equal to n term and rewrite this. So you get this new formula. AN star is n factorial minus, well, this. I goes from 1 to n minus 1, n minus I factorial AI star. But then look, this formula is exactly the same as this formula. I mean, they are exactly the same apart from the stars. So I think I can show them now. Apart from the stars, they look like the same. So the same kind of recursion formula. Well, initial values are the same, but then it's easy to see, I mean, inductively that my star sequence was indeed the ANs is equal to ANs for all n greater than or equal to 1. With, of course, the exception of the first one where B0 was 1, but not a problem. So, well, then I can explicitly write x over pi x. So x over pi x is, now I want to write everything explicitly here. So there is this first term. So this is logarithm of x and minus k goes from 1 to m minus 2 ak over log x to the k minus 1 and the error term. Okay. Error term. So I got this formula where now it's very significant because AKs are now the number of indecomposable permutations. Okay, so there is this interesting combinatorial connection with the inversion as well, and it makes sense. Well, since pi x is like about x over log x, x is cancelled, and that's the main term. So you have to start with log x. But then there are these other terms, I mean, secondary terms here that comes into the game. And well, they are dictated by some combinatorial objects, as you can see, which is very pleasant to see. And this formula you can use for any m greater than or equal to 3 as x goes to infinity. That will serve you as an asymptotic formula where AK is the number of indecomposable permutations. I think I have achieved my goals. So there's really interest in these things. But let me also show you one final thing. So remember, we had the derangements. So let's make some connections. So dn over n factorial. So just divide by n factorial in that formula. So note that dn over n factorial is this sum, but you can take the limit of that. So limit as n goes to infinity of dn over n factorial, but you can see that that's 1 over e. I mean, that's really the power series of the exponential evaluated at 1 when you let n go to infinity. So you get 1 over e. So that's the ratio of the number of derangements to the number of all permutations. So that's 1 over e. But now, from Comtet's result, we also know that an over n factorial, that limit is 1. So I think we can take the ratio. So that's a nice object to look at. So the indecomposables over the derangements. So if you look at the limit, you get again e because of this 1 over e. Okay, so I think at the beginning, we got e from somehow the prime number theorem. Okay. But now I got another way now. So E is related, for example, to this quotient. So the ratio. Now that's another probably nice observation here that comes out of this thing. Now, of course, you can say that then in the limit, since E is bigger than 1, ANs should be more than the DNs. Okay, E is a number bigger than 1. So ANs should be more than DNs. I mean, if you look at the statistic here, the data, I mean, it seems that after 3, okay, D3 was less than A3, D4 was less than A4. I mean, you can see that it always holds. I mean, how can you prove that, for example? How can you show that Dn is always strictly less than An when n is greater than or equal to 3? Well, it's not easy to prove it. It's not trivial from the limit, right? Limit will not give you that because it will tell you when n is large. Now, but you can do the following. By the way, I should say that indecomposable permutations have other applications. They are used in coding theory, for example. And a form of a code, which is known as the gray code, uses the construction of gray codes uses indecomposable permutations. And the mathematician who did that first is King. Okay, so King has a paper in coding theory and who definitely used the indecomposable permutations. And at the same time, he proved this interesting theorem that the number of indecomposable permutations for all n greater than or equal to 1, that's what's nice about this, is always trapped between, of course, this is trivial. An is definitely less than or equal to n factorial, but that's the content of his theorem. An is always greater than or equal to n factorial over 2. Okay, so that's what's interesting about this. So he proved this. And I tell you that it's not trivial to prove this. So he used, you have to use a little bit of a trick from combinatorics. You cannot easily prove it from the recursion, for example. I mean, it's not easy to see it from these analytically, but he has a cute argument somehow using reflections of indecomposable permutations to do that, a clever argument. Nevertheless, he proved this. But when n is greater than or equal to 3, let's look at derangements. So you see, well, I have to look at this part. When n is greater than or equal to 3, this is an alternating sum. So it starts like this. First of all, the first two terms cancel. It's just 1 minus 1. Then you have a 1 over 2. And then since n is greater than or equal to 3, you have the case n is equal to 3 term at least. So it will be minus 1 over 6, and then it will alternate. So it's obvious to anyone that this will be less than 1 over 2. So then the ratio of dn to n factorial will be less than 1 over 2, but an definitely is greater than or equal to that ratio. So when you combine these two things, this easy observation and King's result, and we confirm our observation here that dn is always less than an for n greater than or equal to 3. So it's really a rich subject, definitely. It's full of interesting connections. And really it comes from the asymptotic expansion and the structure that surrounds that. By the way, there are other functions that we use in the study of primes, but they don't have this nice structure. They don't have such expansions. And so that's why it's nice. I think it's a nice property of the prime counting function that it can be connected to combinatorial objects in an interesting way. I mean, before I prepared this talk, I didn't know that such things would come out. But if you are patient enough and work it out, things happen. I mean, even miracles happen. So I think I convinced you. I mean, this was an expository talk. I mean, this is not a research type talk, but just showing you that it's interesting. Okay, so, and I did some, of course, I did some work on these, but I just wanted to share these with you. That's all I wanted to say for today. I think I can stop at this point.
I think we have a question in the chat box, and it asks, why did we choose n equals 5 instead of any other number?
Yeah, because we could choose other numbers, but then things don't cancel. when we look at such combinations. I mean, we see that they don't cancel out, and we don't get the inequalities that we want. I mean, that was probably Ramanujan's insight, and he saw that that case was working. So, so you have to try and see if the computation gives you what you want. I mean, anything significant. Sometimes it will not give you anything, okay? Because things will not cancel out, okay. Okay. So if you're asking where is this applied in technology, of course, I said one thing, in coding theory, for example, the indecomposable permutations are used in coding theory. I am not a researcher in coding theory, but I have seen papers like that. So it's important. In fact, the combinatorial part becomes important even in coding theory. But I haven't prepared anything significant on that. Okay.
I think these were the all questions, and if it's possible for everyone, we can switch to second talk.
Okay, thank you for listening.
Okay, thank you very much.
Thank you very much.